Now that you're experts at the equations for the 555 timer and how to use those to calculate frequency and duty cycle, let's take a look at a couple of examples. The first one's going to be very straightforward. What I have is a 555 timer where I'm giving you the resistors and the capacitor values. So I'm given this right here. R sub A is 390 ohms, R sub B is 180 ohms, and the capacitor is at 6.8 microfarads. And I want to calculate the period, the frequency, and finally the duty cycle. So I've kind of set this up. I have the values in here and I have the equations. These are the equations that you need. It's for the period, it's 0.693 times whatever the value of resistor A plus whatever the value of resistor B is, times the capacitor value. And the resistor needs to be in ohms. The capacitor needs to be in farads. So that's going to be a problem. I'm not going to multiply by 6.8. I need to actually get the value for that, which is going to be 6.8 times 10 to the negative 6, because micro, the prefix micro means 10 to the negative 6. So when I plug this into the calculator, I'm going to be able to arrive at the period is 0.693 times 390 is resistor A plus 2 times 180 times, and like I said, instead of 6.8, I need to multiply this by 6.8 times 10 to the negative 6. So I'm going to put in 0.693, and I can use parentheses because the calculator understands that that's a times. And my first resistor value was 390. The second resistor, and I need to double it, is 180. And then I had for capacitor value 6.8. And second, this EE is the same as doing times 10 to the whatever power, and that power was negative 6. So when I get this, the value I receive is 0.003543, or 35343, which is the same thing as, that's in seconds. So when I get that value, it's in seconds. If I want to convert that or no, it's not whether I want to or not, I need to convert that to milliseconds, because I don't want to have a number with a decimal like that. I want the number to be something between 1 and 1,000. So when I move this 3 decimal places, what I'm going to get is 3.53. Make sure you're always rounding correctly when you do this. I went 3 places to the right, so that ends up being milliseconds. So my answer is actually 3.53 milliseconds for the period. Now here's what I was saying in the other video and have up here above about calculating the frequency rather. Typically I'll have people say, okay, the frequency is 1 over the period. They are inverses of each other, and they would typically try to put that in as 1 over 3.53. That would be incorrect. I need to make sure that I include in that the appropriate exponent. So what needs to be as a part of that is times 10 to the, we went 3 places, negative third. Okay, or I could do 1 over 0.00353, however I wanted to do that. Either way, the nice thing in the calculator, again with the TI-84 models, is this little x to the negative 1 button is really handy. I have that is there's my answer. I can say answer to the negative 1 power. That's the same thing as inverse. Raising a number to the negative power, it means flip your fraction over. And so when I hit enter, I find out that my frequency is 282.9 cycles per second, okay, or hertz. And since that number is less than 1,000 and greater than 1, there's no point in me moving it. I don't need to change it to milli or kilo or anything else. I can leave it as it is. And so my frequency ends up being 282.9 hertz, straight up. The last thing I want to do is I want to calculate the duty cycle, and that is my time high over the entire period. The time high was that part of 0.693 times RA plus RB, and without the 2 in front of it, over the period, which is 0.693 RA plus 2RB Okay, if I'm going to do it that way, I need the capacitor on the end. This is what I said in that last video. The numbers all cancel. 0.693 divided by 0.693 is just 1. So this right here is what I end up for being my duty cycle. And we actually like to multiply it by 100% so that we show, instead of being given as a decimal number, it's given as what is the percentage of time that my signal is high or sitting at 5 volts. So again, I just plug in the numbers. I get times 180, or I'm going to go ahead and do that math. That's 360. So I kind of simplified that one out. Again, if I do that with the calculator, and I can do it just like it looks, parentheses are important because of the order of operations. Close parentheses. And I get 0.76 when I multiply by 100 is 76% duty cycle. So there's my 3 answers for this straightforward question. That's rarely the way that you're going to be presented a problem as an engineer. Typically, you might be presented a problem a little bit more like this, where you say, we want a duty cycle of 60%. So that's what I'm looking for, and I want a frequency of 2.5 kilohertz. This is a little bit more involved problem than what we are typically used to. So here again are your 2 equations, the ones that are important to us, and we want to go through here and look and see what it is that we know already. We know the duty cycle is supposed to be equal to 60%, so I'll go ahead and make that a decimal. It's 0.6 or 0.60. And we also know that the capacitor value is given to us as 0.47 microfarads. So we know the capacitor is, and I'm going to go ahead and write this in engineering notation, it would be 0.47 times 10 to the negative 6, but if I try to write it in the best notation I can, it's 470 times 10 to the negative 9. I don't know what resistor A is, and I don't know what resistor B is. If I go back to the very basics of Algebra 1, well, not the basics of Algebra 1, it's about midway through the year, one of the things you need to understand, or you learned, was if I have 2 things that I don't know, then I must have 2 equations. Fortunately enough, I actually have 2 equations here, and I can go through and I can work with and manipulate those a little bit. And I have 2 equations, 2 unknowns. I can find out what those are. So let me plug in numbers here for a moment. I'm going to say 0.693 times RA plus 2RB times my 470 times 10 to the negative 9th. That equals, oh, I also know what my period equals, or I sort of do. My period is given to me in the frequency. The frequency was supposed to be 2.5 kilohertz. So once again, I need to figure out what the period is. The period is 1 over the frequency, which is 1 over, and I'm going to say 2.5 times 10 to the 3rd. That's what kilo means. And that's going to give me, again, in engineering notation, 400 times 10 to the negative 6th. And so that's what this equation here needs to equal to. Change colors again. And then the next step would be I want to take all these things that are actually just numbers and I want to combine them together. So I'm going to multiply 0.693 times 470 to me is 325.7 times 10 to the negative 9th. And I still have the RA plus 2RB. That didn't change. And then on the other side, I still have the 400 times 10 to the negative 6th. And so then solving for trying to get RA and RB by itself, I'm going to divide both sides by my 3.25 times 10 to the negative 7, or negative 9th rather. And what I'm going to get when I finish that is I'm going to have RA plus 2RB, and that is going to be equal to 1,228.09. And the answer better be ohms, because so that's one equation. I have one equation with RA and RB in it that I need to work with. The second equation is going to come from my duty cycle. It's much more straightforward, and I'm just going to write that out. So I have RA, and I can multiply both sides of this equation by the denominator. That's, again, when I try to get a variable by itself, I want to get rid of the fractions usually. So I'm going to multiply, and I'm actually going to show this one. So I'm showing that I'm multiplying both sides by what's in the denominator of my fraction here to essentially get rid of it. It'll cancel out that way. And the parentheses are important because I need to multiply everything on the right side by 0.6. Everything that I multiplied here needs to be multiplied by 0.6. So I'm left with RA plus RB on the left. On the right, I have 0.6 RA plus 0.6 times 2 is going to give me 1.2 RB. Just get all the stuff on one side that's RA and all the stuff that's on the other side that's RB, and then I can take it. One of the ways we have for solving two equations with two variables in it is substitution, which is exactly what I'm going to do. I'm going to subtract RA from each side and RB from each side. I'm going to subtract them both. So I'm going to have 0.4 RA equals minus 1 there is going to be 0.2 RB. And I'll divide by, it doesn't matter which one I divide by. I'm actually going to divide by the 0.2 because I want to get rid of all my decimal numbers and fractions. So I'm just going to go ahead and do that and divide out by 0.2. And what I'm going to find is that RB is equal to twice RA. Now I can take this, and I can take 2RA, and I can plug it back into my equation number 1 for RB. This was actually my second equation. And when I do that, I'm going to get RA plus 2 times 2RA equals 1,228.09. And put everything together, and I have 5RA equals this same number. And divide finally by 5, and I find that RA is 245.6. And this is resistance, so my units had better be ohms. And so there I found what RA was. And if I now want to know what RB is, I'm going to take that value and plug it back into my second equation, and I'll find that RB is 2 times 245.6, which is 491.2 ohms. And there I found the values for RA and RB that would give me a 60% duty cycle and a 2.5 kilohertz frequency clock operation, assuming that I have a 0.47 microfarad capacitor. That's the way you work these. These are the kinds of problems you'll be working on the activity today and do this. And we will be using, or could be using, the 555 timer throughout the year. Being able to do these calculations will help you be able to set up the kinds of frequencies that you need as you work on some of the other activities. Also, make sure you go into Moodle and take the WSQ quiz. I've got some questions on there. And if you have any questions, then I can get those questions there and we can talk about that at the beginning of class.